First in line, we have another lady. She's a backend developer and a data engineer with over 5 years of experience working mostly with Python and Django. She enjoys building reliable systems, improving data processes, and designing APIs that make things work smoothly and efficiently. A lot of work involves optimizing code and making sure everything runs without issues. Please join me in giving a warm welcome to Florina Ahmeti, Python web engineer at Valtech. She will be sharing her insights on mutation testing, a helpful technique that makes code stronger by testing how well it handles unexpected changes. Florina said she enjoys problem solving, learning new things, and sharing practical ideas with the others.
Thank you.
You go ahead.
Hi everyone, and hi for the very great introduction. I sound more amazing there, definitely. And the topic that I want to talk about today is from code coverage to code confidence, which sounds pretty sales pitchy, but I'm not trying to pitch a topic here. I'm just trying to introduce this topic to the community so more people work with it, and hopefully it will develop more in time, since right now it's relatively new and it does not have a great community. So I guess first things first, again, I'm Florina Ahmeti. You can find me on LinkedIn. And well, I guess anything you want to talk to me about, you can contact me there. When it comes to my experience, I worked with Node.js, Angular, PHP, WordPress, and then I switched to Python and data engineering, and never in my life would have thought that I'd be talking about testing in a conference. But I had an issue. I did not like writing tests at all. And when writing tests, usually I would just get it done for the sake of getting it done and the pipeline passing. I think many people here do that. But I had an issue because as we know, projects have different functions, APIs, and everything, and when you touch something, there is a chance that you can break something else. And that's what I did. And when I did that, we had a CI/CD, and hopefully that failed, and the code did not went to production. But that made me think, is there a way that I can detect that I'm breaking the code before actually going it to the pipelines? And when I thought about that, Mira also just started talking to me about testing, which is my team lead. And when we talked about it, he introduced mutation testing. When we talk about testing right now, we have a lot of tests, as Maria also mentioned. We have unit tests, regression, integration, and everything. But for me as a developer, unit testing was the most important. And the current testing process is unit testing, plus to make sure that everything is working fine, we have added test coverage, which in theory, test coverage is pretty good. We make sure that every line of the code that we have written, it's executed. But making sure that a line of code is executed does not necessarily mean that we have verified its functionality. And that's where mutation testing comes in hand. Let's say we have this function here. We have the get shipping cost here. If the order total is greater or equal to 50, return 0, and if else, return 5. And then we have this test, and we are asserting that the shipping cost is 49, and we get a return of 50. And then if the shipping cost, like if the total of the order is 60, the shipping cost is 0. What is the code coverage in this case? It's going to be 100. Okay, guess here. It's going to be 100 because we touched the if condition, we touched the return 0, and we touched the return 5, which our test is verifying that everything was executed and working successfully. But that's not every time the case. Well, initially, when mutation testing it was introduced to me, Miro asked me, do you know what it is? And I know mutation, and I know testing, I mean mutation, mutant ninjas and everything, and then testing, but I didn't know what those two combined mean. Well, in programming, mutation testing is simply another metric, which in comparison to measuring if every line of code is actually executed, we are measuring how efficient those tests are. So we try and measure if the functionality is verified. How it works, it's by applying different bugs into our code base and then executing the unit tests. If all of the tests were planned carefully and thoughtfully, then a simple bug introduced to the code base shouldn't actually change the outcome of our unit tests, so the test should fail. But if it does not detect that, then it means that we can introduce bugs into production without even knowing that we have them there. Okay. If we take this example, we have a simple method to classify a number, which is greater than 0, less than 0, and 0. If we take this test suite, we can check if number 5 is positive, which we know it is, and we can check that the -3 is negative, which we know it is. But what if later on in the code base, we actually did a change like this to the code? If we change this simple operator, this test would again pass, but we can clearly see that the functionality is not what we want, because in this case, we would classify that number 0 is actually a positive number when we want it to be simply 0. To do that, to verify that and to make sure that no one is going to break this in the future, we can simply add a new assert to the test and verify that 0, when we get 0, the response is 0. So if in the future we do this, our tests are going to fail, and we're going to verify that that's not going to be an issue. Talking about mutation testing, I want to introduce the basic concept of it. We have mutation operators, which are those tweaks, so making greater than to greater than equal, substituting a plus with a minus, etc. We have a mutant, which is basically applying a mutant operator to the code base. That's a mutant. And then we have survived mutant and killed mutant. Survived mutant is basically code or a bug that was not detected by our unit tests, and killed mutant, it's something that was killed by your unit tests. So that's what we want to achieve. We want to kill all of the mutants. One of the issues of mutation testing right now, equivalent mutations. Sometimes you can apply different mutation operators, and those will give you the same result, which would mean redundant work. These are simply a few examples of mutation operators, and here you have a pretty long list of other operators that we can define. A lot of libraries that are currently with mutation testing, they have their own operators, but they offer also ways to create your own mutants for your own uses. Our starting point to use mutation testing would be here. We have our test suite, and we have our original code base. What mutation would do is get the original code, generate the mutants, so we have multiple mutants for the code base. After that, for every mutant that we have generated, we run the test suite, and if the tests basically fail, we have killed the mutant, and if it has survived, then, I mean, we don't want it to survive, we have to move forward and improve the tests. sometimes you need to improve the tests, and sometimes you actually need to improve the code base. It would all depend of the mutant that survived. Okay, so what are the mutation testing goals? We have two main goals. One is coverage analysis. So instead of testing if a line is executed, we want to check if is a line executed correctly, or if the functionality is actually verified. And the other thing is to detect unnecessary code. If we apply different changes to the code base and the test suite all pass correctly, when analyzing those, you can find that you actually have that code into your code base, which is not doing anything. No test is testing that. You can detect those gaps also. Mutation testing, it's a general topic, so it's not only for Python, it's for different languages. And there are different libraries that have been worked on. In Python, we have Mute and Cosmic Ray. For C# and Node.js, we have Spark. And then for Java, we have PyTest. And basically I think for every language that there was a library or a tool that you can use to test mutation testing. But I'm a Python engineer, so I worked with Python. Well, as I mentioned, there are quite a few libraries in mutation testing for Python. There is Cosmic Ray, Mute, and MutePy, each having its gaps and its advantages. As I said, the topic is pretty new and pretty not really famous with the community. But every other library tried to solve an issue, but they all had their gaps, and when analyzing them, I actually decided to move with Cosmic Ray, since it offers more configuration options for the code base. It provides parallel execution, since we're going to see that mutation testing can actually be very slow. It offers the flexibility to run in parallel, but it's also slower due to the complexity of its operations. But on the other upside, it offers option to filter out operations that you don't want and you don't need, so you actually can sacrifice something and gain something else. How it works, it's pretty simple. We install it via a package manager. We create a TOML configuration file, initialize a session, which what would do is would create an SQLite file, which would hold all of the data for the mutations that are applied. And you simply run Cosmic Ray. I mean, I'm saying simply, but it's going to take some time based on the mutants that you have. And you can generate a report after that to see what went wrong and what went right. Okay, so I want to have a short demo with you guys so that you can just see it in action. Here, it's a basic configuration file, how it looks into the code base. So you would have a module path, which would be the name of the module, of the folder, or the repository that you want the mutation test to be executed. You have a timeout, which would mean how much time are my tests allowed to take to run this. In case a mutant generated an infinite loop, we want to terminate the process after 30 seconds in this case. We have the excluded modules. I don't want to mutate tests, and I don't want to mutate migrations, and I don't want to mutate certain parts of my project, which may be boilerplate from the library, so I'm going to exclude them here. You have the test comment, so whether you use PyTest, Unitest library, is going to be, you can just simply change it here. And then the distributor, right now I have a local distributor, which would mean I would run only one worker to run those, but I can simply have an HTTP worker here and then run them. As I said, okay, I have them here. By running this Cosmic init tutorial, blah, 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 I'm going to create a database which would look like this. So the database is pretty simple. It only has 3 tables: mutation specs, which are which file the mutation is being applied, which operator, and then these are the starting position and ending position of the operator that is going to be changed. And then here we have the work results, basically the results of our tests. If I run this, which I'm not going to do it right now for you, I'm going to get a report like this, which here would look something like this. Well, if we see here, we have, we have surviving mutants, 76 surviving mutants, which is not really good. It means that a lot of changes in my code were not detected by my test suite at all. And if I check the job list here, I have the outcomes here. So what was changed? This was the original line of code, which is some loan calculation minus blah, blah, blah. And then from the minus, we changed the operator here to plus. After changing this, our tests passed successfully, which means we are not testing this case at all, and we're not making sure that the pre-contract data total cost is actually being, is having it subtracted, yeah? The deposit instead of added. So that's one thing which I don't want. And in this case, what I would do is go and add the test to actually confirm this case. If we check for a mutant that was killed, so was successfully, I can check here. So I caught this case of changes, which means that I'm testing this case successfully, but not the other case. So I need to add a new unit test to fix that. We can go through other jobs, but I think I'm on a time limit, so I'm not going to do that. I'll simply continue with my presentation. You saw so far how that works, and as I've been mentioning, there are quite a few challenges. It takes time to execute. This would mean that if your test suite ran for around 10 seconds, and we did a small change, we applied a mutant, then that mutant was applied around 100 lines, then that would mean that the time it would take to execute it would be 100 times 10 seconds, which would mean some very much seconds. And but there are workarounds around it, so it cannot make it very seamless. It still can decrease the amount of time that it takes for execution. And then the other thing is we have false positives. For false positives, I use Cosmic Ray especially for this reason, because it can offer us different filters that we can work with. It's the CR filter git. So basically, if I'm going to commit into a branch and I'm going to create a merge request with dev, it's not going to apply mutants to all of my code base. It's going to apply mutants only to the code base that I changed. The other thing is excluded operators. So if I'm not having a lot of loops or if statements, I can just simply say that I don't want the mutants to change, past statements to continue, etc. And then there is the Cosmic Ray Spore filter. So if you have just a piece of code inside your code base that you want to ignore the mutation, then we can use this, which is an extra library, and you can add a comment on top of whatever you want to exclude, and a comment at the end. And this library would help detect the start position and end position of what you want to ignore, so it does not apply mutants there. Okay. After the challenges, I want to talk about how this would be as part of the workflow. As part of the workflow, I thought about different ways on which we can integrate it, and I know of different companies that have integrated it as part of their pipelines, but my favorite is to run it as a scheduled job in a time interval. So it's not something that you would want to execute multiple times a day, but I would want to confirm at least once a week. So you can simply run it as a job during the weekend, and on Monday you can check if there was a new mutant that has survived. Run it as part of a pre-commit library. It's pretty simple, but this would be a bit of a hassle if it takes long. And then have it as part of the CI/CD pipeline. It's pretty good, but again, if I want to test something on dev in 10 minutes because the QA is waiting, I would not want to block the CI/CD pipeline. And then we can integrate it as part of the code reviews and developments. This would be in good faith of each other. So basically, we have a convention, then every time before we code review, we check this as well, but I'm not sure that that's the best way to do it. Well, why should we use it? First is because it offers code confidence. Since it's going to challenge your test suite to catch subtle bugs that you may not even think that you have them, it's going to give you more confidence in your code, and it's going to ensure higher quality of tests and code base. The other thing is that it identifies gaps. So surviving mutants will highlight your gaps into the test suite. So, well, that would help, of course. And then we have encourages best practices. Since you're going to keep in mind that we are going to run mutation testing, I definitely would not want that to fail since it's going to take longer to run. So I'd be more thoughtful when I did my tests, when I wrote my tests, than just not having them there. In the end, I want to say this quote, which resonated with me. Which is, it's hard enough to find an error in your code when you're not looking for it, but it's even harder when you're not looking for it. So if we all guess that everything is working fine, it's going to be way more harder to find something that's not working. So that's that. Thank you.
Thank you.
Questions?
Any questions? Please raise your hands. Okay. We'll go first on that end over there. We have one guy raising his hand in the yellow row. Okay.
Can you hear me? Okay. So I wanted to ask, how does the Cosmic Ray library or mutation testing deal with crashes? So if while testing it, it changes some symbol and while the tests are running, the program crashes. How does it detect that? How does it handle it?
Actually, as I mentioned, all of the ways that I mentioned to test, to basically integrate it as part of the workflow here, here, are after the actual development because, as I mentioned, running Cosmic Ray would create a database for you. So it will initialize a session, and that session, unless you overwrite it, again, it will not change. So if I have one session right now and I put it as part of my repository, and after a week I did changes to that code, the same mutations would run again. I need to initialize the session and then run it again for it to detect those changes. So if you do something to your code or the tests, it's not really going to interrupt this process. I'm not sure if that was okay.
Yes, but it was more focused. For example, I'm guessing that on the mutation testing, it can also run, for example, I apologize, but like indexing. So if we're doing something with tuples, and instead of first index, it goes to the second index. Mm-hmm. And if we have multiple types of data, and it produces like a type error.
Okay. Sorry. Well, that's going to throw a type error, and that's going to stop the execution of the tests. That would mean that you have a survived mutants there because, well, an error was thrown, so it's going to detect it.
Thank you.
You're welcome.
I'm afraid we don't have more time for questions. I know that Erenis here had one, and a person over there, but feel free to find Florina after the presentations and ask her as many questions as you want.
Yes. Thank you very much.
Thank you.